I want to clear up a loose end or two that will help you with some of the homework problems. And one of them is about the capacitor energy. This is the energy stored in a capacitor. This is one equation for it. There's actually another one too, and it is where C is the capacitance, and Q is the charge on the capacitor, and V is the voltage drop across the capacitor. So if you have, since Q is equal to CV, you can rewrite this equation, and you'll see that these two are equivalent. What does this mean? Well, as you saw, there's energy stored in a capacitor when it's charged up. There's charge on the one side and the opposite charge on the other. The fact that these charges that are here have to pass through a wire or something, and then perhaps they could light a light bulb or a light emitting diode, as you saw. That takes energy. So as this happens, these charges basically drain off here, come over to here, cancel everything out, and in the end, you have a capacitor with no energy because the energy ran through and lit the light bulb and then became heat and went away. But how much energy is in there? Well, clearly the greater the voltage, the greater the amount of energy, because the greater voltage means you have more charge on each end, on each side of this plate for a given size capacitor. And also the larger the capacitor for a given situation, the more energy, because a larger capacitor can potentially store more charge. I'm not going to derive this equation for energy, but I will show you that the units are correct. Let's see, units of energy, as you know, are the joules. And here we have units being equal to farads. So a farad times a volt squared. Well, what's a farad? Well, I like to think of, I'll go back to Q is equal to C times V. A farad is the unit of capacitance, and it is equal to, since C is equal to Q over V, if I divide both sides of these by V, I'll get this equation right here. A farad you could think of as being a coulomb per volt. All right, so let's go back to the original equation here. Units of energy. So therefore, let's see if a joule is equal to a coulomb per volt, which is a farad, times a volt squared, which is just this equation up here, brought down to here. Well, let's see. A joule is equal to, so if I multiply these two, I'll cross out one of those V's. It's equal to a coulomb times a volt. And a volt, another way to think about a volt, which we've talked about, unit of a volt is joule per coulomb. We talked about that a couple of videos ago. So therefore, joule, is that equal to a coulomb times a joule per coulomb? The answer is yes. So all I did here was to show you that this equation here makes perfect sense for being joules, which is the unit of energy. All right, and when you're doing a calculation for this, just make sure that your capacitor is in farads. So if it's 6 microfarads, it means that's equal to 6 times 10 to the minus 6 farads. And of course, this is volts, and your volts are usually numbers that are reasonable, 3, 4, 5 volts. But make sure that those are the units you're using in your calculation when you find your energy. And you should get a reasonable answer. It'll be a small number of joules for a given sized capacitor. All right. And the other thing that I wanted to make sure that was clear for you was that when you have capacitors, we talked about parallel capacitors. When you have capacitors in series, I mentioned in an email that if you have a certain amount of charge on a certain capacitor, let's say this capacitor here, they don't even need to have the same values. But let's see what happens if I put a positive charge on this capacitor, and I'll call that charge Q, plus Q. Well, that means on the opposite plate of the capacitor, there has to be a negative charge. So this would be negative Q. But if you look at this situation right here, between these two capacitors, this is kind of like an island. You can't have charge jumping across either side of this capacitor. That can't happen. Just can't happen. So whatever is on the left side of this capacitor here, the opposite has to be on the right side because it has to balance out to be 0. So that means that on this capacitor here, next one in series, it also has to have plus Q on it, no matter what size the capacitor is. And the negative side correspondingly also has to be negative Q. You could say the same thing about this one over here. Next one down, this side here has to be plus Q. And then the next one has to be minus Q. So capacitors in series, the moral of this story is, capacitors in series all have the same size charge on them. All right, so they won't have the same voltage, of course, if they're different valued capacitors, because the voltage for a capacitor, since Q is equal to C times V, you could say the voltage on a given capacitor is equal to Q over C. Since they all have different capacitances, they're all going to have different voltages across them, in this case. And I think I'll stop there, and I'll do another video or two on calculating parallel and series capacitances and showing you the equations for that.